Gas concentration in the plasma is approximately 3 milliliters, or I'm sorry, 0.3 milliliters per 100 milliliters. That's assuming a healthy functioning individual with a partial pressure of oxygen in the arterioles equal to 100 millimeters of hemoglobin. That's not very much. That's not enough to keep us alive. Now, as I mentioned previously, we do need that oxygen dissolved in the plasma if we're going to get gas exchange with the tissues. So it is critical that we have at least some of it there. But we also need a mechanism to transport a considerable amount of oxygen in addition to the amount that is dissolved in the plasma, and that's where hemoglobin comes in. If you take a look at the figure on the right, you can learn some rather interesting things from this. At a partial pressure of 100 millimeters of mercury in the plasma, we have our 0.3 milliliters per every 100 milliliters. But if you look at the amount that is bound to the hemoglobin at the same partial pressure, okay, partial pressure of 100 millimeters of mercury, we have 20.0 milliliters of oxygen per every 100 milliliters. So a lot more oxygen bound to the hemoglobin. When bound to hemoglobin, we call the hemoglobin oxygen complex oxyhemoglobin. It's you can think of it as a chemical reaction, and therefore a new molecule. So if we were to consider the reactants as hemoglobin, abbreviated HB, plus oxygen, we would end up getting HbO2, so that's my oxyhemoglobin. Fortunately, this is a reversible reaction, okay? And we're going to be talking about this process in detail. The free plasma or free oxygen would be in the plasma. Okay, so you can consider that as being plasma dissolved oxygen. Hemoglobin is a fairly special molecule, and I know that we talked about this to some degree when we talked about in our hematology lecture. Hemoglobin contains 4 different peptides, 4 separate peptides that would be synthesized separately, but then they bind one another through covalent and ionic and hydrostatic bonds, hydrogen bonds. And these hemoglobin molecules contain 2 different subtypes. Each of them have an alpha and a beta. Those are the 2 different subtypes. And I should say most adults have those particular subtypes. Fetus, so fetal hemoglobin, actually has, instead of alpha and beta, it has gamma and delta. What's the symbol for delta? I think this is the symbol for delta. And so those are slightly different types of hemoglobin peptides with a higher affinity. If you think about why a fetus would have hemoglobin with a higher affinity, I'm hoping that you kind of turn that over in your mind and you think about that and you understand, after thinking about it for a few minutes, that the reason the fetus needs a higher hemoglobin is because it actually, or a hemoglobin with a higher affinity, is because it actually needs to essentially wrangle away the oxygen from the hemoglobin found in the maternal blood. And so most fetuses change as they develop and they get closer to birth. The type of hemoglobin that they will produce will change so that they, as they become a breathing organism, instead of reliant specifically on their mother for their oxygen supply, they then have the alpha and the beta hemoglobin. Every now and then you get some interesting adults that actually still have fetal blood. They still have a normal life. It's totally fine. It doesn't affect them negatively. Their hemoglobin just happens to have a higher affinity than the average individual. Each hemoglobin molecule carries for oxygen, and that oxygen binds to what is known as the heme group. In the center of the heme group is an iron atom. Okay, an iron atom. And iron is an interesting molecule. It easily goes through oxidation and reduction reactions. So it can be oxidized or it can be reduced, and it will go back and forth based on the level of oxygen present in the blood. So when oxygen is present, oxygen will bind to that iron, creating iron oxide, and then it can also release the iron when the oxygen levels are low. Hemoglobin is very highly concentrated in the red blood cells, and in fact each red blood cell, this is kind of mind-blowing, each red blood cell has 280 million hemoglobin molecules. If you consider how many red blood cells we have in circulation, that means that we are capable of carrying over 1 billion oxygen molecules. And that's pretty cool. That is just mind-blowing to me that we have so many molecules bound to these hemoglobin molecules floating in our bloodstream, trapped in the red blood cells.